Hello, my name is Matthew Bailey, and I'm introducing the Spatial Stream Network's SSN applications with the BC Freshwater Atlas. So the why and the inspiration is we need better tooling and infrastructure to efficiently work with stream network data, especially within BC. Summarizing environmental attributes across stream reaches with GIS and statistical models can be challenging. Spatial autocorrelation patterns often reflect the branching networks with upstream and downstream hydrological connectivity and varying flow volumes at the confluence of tributary and main stem reaches. Conventional GIS tooling such as zonal statistics and intersections and conventional statistical models such as regression often fail to account for these features when working with stream networks. SSN, or spatial statistical stream network models, have been introduced for some time um, and offer a set of advantages to help with some of these issues. SSN tooling was originally developed by the U.S. Forest Service, NOAA, USGS, and other groups, with a panel there at the bottom with some of the key developers. SSN models are a special class of statistical tools for regression that are specifically designed to incorporate network connectivity, flow direction, and flow volume. Sites can be considered flow connected or unconnected with different types of relationships. SSN models are used to model a variety of parameters with within statistical and correlative modeling approaches. So some common examples of SSN models in practice include empirical models to predict stream temperature across stream reaches in larger basins. However, many other applications exist to predict various water quality parameters like conductivity, pH, geomorphic metrics such as riffle run sequences, aquatic biota, and so on. Basically, anything that you can model with a standard regression equation across stream reaches in a stream network can be turned into an SSN model. SSN models often, but not always, show better fit and performance, predictive performance than standard regression models. So on the left here, we can see an example of a stream temperature model where the predictions are actually modified, updated, and leverage existing site data. At the bottom, we can see an example of where they, with electrofishing data, used SSN models with a series of reach level attributes to predict trout densities and species occurrence. The little text boxes here on top of each image shows the change in fit between a standard basic regression model and a regression model that uses the SSN structure. So despite the adoption and despite all the benefits of the SSN models and tooling, the adoption and use cases of SSN models in Canada remain limited. So why is this? Custom stream network development, i.e. starting from scratch with a digital elevation model with poor linkages to existing hydrological data sets can be a big burden to individuals wishing to use these models in Canada. So this means working with a digital elevation model, filling it, correcting sinks, voids, lakes, water bodies, and so on. It's also difficult to generate meaningful environmental predictive variables and often requires bringing in custom external tooling. Additionally, manually snapping sites onto synthetic stream reaches also involves associated QA/QC, which can all be pretty time consuming. US applications can readily leverage the NHD Plus stream network, as well as applications and tools such as StreamCat with hundreds of pre-processed reach level variables that can be used as predictor covariates in regression. So what are some opportunities and solutions for BC? Oops. In BC, this project is focusing on integrating the Freshwater Atlas, or the BC Freshwater Atlas. The BC Freshwater Atlas is far from perfect, but it's still seen as an authoritative cartographic source for freshwater features in BC. The BC Freshwater Atlas contains all necessary features for SSN modeling, but in its raw state, it requires heavy-duty pre-processing. So the project objective here is, can we leverage the BC Freshwater Atlas with additional tooling to make extensions for SSN stream network modeling? And in this project, I'm going to show you how we go about and do that. So what are the required formats we need for SSN models? The structure is pretty simple, but it's quite strict. So you need your stream reaches, also referred to as edges or streamline geometry. And then each stream reach needs its own lateral drainage polygon, so showing the drainage that flows into that stream reach, and these are called reach contributing area polygons. There's also nodes that specify whether a stream reach is a first order end node, a pseudo node, so like a stream reach in a long linear network, or a confluence node. Um, each of these stream reaches and RCA polygons need one-to-one relationships and have to approximately represent the proper hydrological geometry there. Previously, these features and tools were generated in an ArcMap package called STARS, which is now defunct there and been replaced by newer tooling. So the process is not so easy. There's many topology issues and underlying differences between the BC Freshwater Atlas and the NHD+. The reach contributing, or the BC Freshwater Atlas initially comes with watershed polygons that to some degree represent the RCA polygons needed for SSN models, but you need to do heavy duty geospatial preprocessing to fix these. So although some of these line up with one-to-one relationships, there are many that aren't directly connected to a stream reach or are polygons that share weird relationships along major mainstem reaches. So in this project, there was a large amount of custom code to fix all of these issues. This relied heavily on iGraph, Neo4j, and some other tooling, which I'm not going to get into in this presentation. But after you do some heavy duty pre-processing, you can generate enough rules and fixes to approximately fix the existing issues so that each contributing area polygon is associated with a stream reach here. So the green RCA polygons and the blue streamline reaches. Yeah, there's the final product there, an example screenshot. We also have to deal with issues with network topology. So that's thinking about the braided reaches, side channels, and so on. SSN models require a structure of dendritic stream reaches, so branching just with two pathways. And so with iGraph, Neo4j, and associated tooling, and leveraging attributes within the BC Freshwater Atlas, we can identify the proper network and routing relationship for the mainstem reaches. We can still bring in the side channels and braided reaches, but for the purpose of the model and tooling, we'll work primarily with the yellow line here. Additionally, too, we still require some custom ruling and fixes to generate these RCA polygons, which can be a little bit challenging in some of the braided reaches where these types of models and tools don't perform their best. Finally, though, after we do all that processing for all the stream reaches across BC, we can generate a database that contains pre-processed analysis-ready SSN objects for the entirety of BC. These include the reach contributing area polygons with all the fixes, the streamline geometry, watershed boundaries, some network index tables, as well as the SSN objects called the landscape network folder and an SSN model folder. You can regenerate these with different sites and prediction points, but the main purpose is all the heavy duty pre-processing has already been done and all the error corrections are fixed and accounted for. And most importantly, these SSN model objects preserve all the existing BC Freshwater Atlas stream reaches. So you can still merge these into your existing projects and mapping applications. Here we can see the linear feature ID for each of the streamline reaches, as well as the associated attributes from the BC Freshwater Atlas are preserved. The next thing we have to think about is bringing in environmental predictor variables. So you can have reach level environmental predictor variables, things that are going on each side of the stream reach, predictor variables that account for factors downstream, as well as upstream basin level predictor variables like drainage area, mean basin elevation, and so on. So for basin level, many basin level regression equations work with area-based metrics and basin level variables. So this can be the drainage area upstream of each stream reach, the mean basin elevation, the road density, kilometers of road per kilometer squared of watershed, the mean basin elevation, and so on. So we need a way to efficiently represent environmental attributes to do these upstream summaries. We need a way to efficiently represent these features at the stream reach level. So that's for each stream reach doing calculations that account for the upstream accumulation. So we're kind of moving from these basin level summaries, which are summaries across a polygon, to reach level summaries that look all the way upstream for each stream reach and report the summary statistic at its outlet. Then we also need an easy, efficient, and repeatable process to generate these upstream basin level variables. So conventional tooling here is raster-based tooling with weighted flow accumulation functions, and there's obvious pros and cons to these, and I won't go into them in this presentation, but that's sort of the standard way. And then the SSN package there also offers opportunity to generate upstream reach level, basin level summaries with vector-based tooling. So this is looking at the upstream accumulation functions by for each stream reach. It looks at all the RCA polygons upstream of that and then uses database tooling to do a quick summary there to give you the upstream variables processed down to the stream reach. So this is similar functionality to an application called NetMap that you might have seen or heard about. So these are high-speed upstream summaries with network and database tooling. To assist with this process, there's several packages out there that do this, but I've sort of been working on my own custom package, which I think is the easiest one to set up here and get going with for doing these summaries for the BC Freshwater Atlas. And the link here is on GitHub, so you can visit and download it. So behind the scenes, this calculation is being done millions of times across all the stream reaches in the BC Freshwater Atlas. So it's for each target stream reach, it knows what's downstream and what's upstream from it. And using database tooling, we're looking at the target reach ID, the upstream reach ID, and then we join on an environmental attribute or variable of interest. And then essentially all we're doing is grouping by the target reach ID to generate these stream network environmental summary statistics. So here's just an example of the Nicola watershed with 4 squares. If you were looking at this for mean basin coverage of the orange square here, it would look like this network pattern here you see on the right. So the general workflow here is identify a watershed of interest, download the pre-processed data from the BC Freshwater Atlas SSN project summary page. I'll put a link to this at the end of the presentation here. Then use this custom SSN environmental summary R package to optionally develop custom basin level variables of interest. And then finally to run your SSN analysis ready model. So you add in your sites, so your stream temperature sites or whatever you're going to use to model, and then you make predictions. And so this workflow of downloading the pre-processed data, adding environmental summaries is meant to expedite and speed up the whole process here. So here's a link to some of the online project resources. So how to download the analysis ready SSN objects, you can access it at this link here. There's also a QR code on the left. And then this R package for SSN environmental summaries here is hosted on GitHub. I'll warn anyone watching this video, this is still a very early beta release. At the time of recording this video, the documentation isn't complete. The FTP download site is also not complete, but specific watersheds can be emailed and made available upon request. Finally, transboundary summaries will not be accurate. So if you're looking at the Columbia or Kootenai River too. It starts and stops again at the border between BC, Idaho, and Washington there. So they'll still have to do some fixes around that. Finally, we can look at some other opportunities that are made possible with stream network models, so we can scale up to province-wide predictions. This is some kind of experimental approaches here. So if we have any like basin level regression equation in the literature, we can transform and apply it to the stream network, as long as we use the same covariates that the original authors use as the environmental predictor variables. We can bring that into this tool and model. So here's an example of a 2006 stream temperature study, and there's a variety of basin level environmental covariates and then fixed coefficients to predict stream temperature. And here what we're kind of doing is we're summarizing these to the stream network and then running the regression equation without too much more modification there. We can also look at things like barriers and fish passage here to identify fish accessible streams, as well as looking at other cumulative effect metrics such as road density here. So this is kind of zooming in on one little watershed here where we can see that each of these predictions show the kilometers of road in the upstream basin divided by kilometers squared of the watershed. Finally, with the SSN environmental summary package, we can also convert the X and Y coordinates, or latitude and longitude, to longitudinal profiles. So this time, the X-axis shows the upstream distance from the outlet of the basin, and the Y-axis shows the elevation. So this is leveraging the Z geometry inside the BC Freshwater Atlas. So it's like looking at the watershed from the side. These types of summaries can be extremely useful to when you're thinking about environmental attributes in terms of runoff, fish accessibility, and fish habitat too. So this is a totally different way of looking at the watersheds. We can also overlay different environmental attributes and do choropleth maps on these as well. Here's another example for the Nicola watershed. Anyhow, so again, this project is still in progress, but here are a series of resources to provide some more info here. And thanks again for watching this video.